What if I told you that every aluminum sand casting you've ever seen started with a tool that never actually touches molten metal, never becomes part of the finished product, and most people outside of the foundry have never even heard of it? Yet without it, none of these castings could even exist. It's called a pattern, and the history behind it is one of the most fascinating stories in manufacturing. Today, we're going to see how pattern making evolved from master craftsmen carving wood by hand to modern CNC machined tooling capable of producing thousands of precision castings. Join us on this multi-part series as we explore the history of pattern making, the technology behind it, and the surprising journey from raw material to finished casting. But first, let's begin where every foundry once started. To understand where we are today, we have to go back more than a century. Before CNC machines, before CAD software, and before 3D models, there were pattern makers. Not machinists, not engineers, pattern makers. These craftsmen spent years learning how to build one thing, the tool that makes every casting possible. This pattern might not look impressive today, it's just wood, but don't let that fool you. A skilled pattern maker could spend weeks, sometimes months, building a single production pattern. And they weren't copying an existing part. They started with drawings, not 3D models, not computer renderings, just flat drawings. From those drawings, they had to imagine the part in 3 dimensions. Then they had to carve it. Every curve, every radius, every angle, every dimension, every one of these surfaces was created by hand. No undo button, no Control Z, one mistake, and you might lose a day's work. And the wood itself fought you the entire time. Every board has a grain. Some are harder than others. Humidity changes them. Temperature changes them. Even the direction you cut changes the result. Imagine trying to build an incredibly accurate production tool from a material that's constantly trying to move. But woodworking wasn't even the hardest part. The hardest part was making something the wrong size so it will become the right size. When aluminum melts, it expands. When it cools, it shrinks. Every single casting, every single time. So, if you built this pattern exactly the same size as the finished part, every casting would come out undersized. Pattern makers had to intentionally make every dimension larger, not because they made mistakes, but because they understood the metallurgy. That tiny amount is called the shrink factor. It's built into every pattern we make. You never see it, but every casting depends on it. It might sound like a small detail, but it's one of the most important calculations in a foundry. If the shrink factor isn't built into the pattern from the very beginning, every casting that follows will be out of specification, and every mold made from that pattern will produce the same incorrect part. Eventually, though, manufacturing had to change. Customers wanted more parts, faster, more consistently, and wood simply couldn't keep up forever. That's when aluminum match plates became popular. Instead of building patterns from wood, foundries cast the pattern out of aluminum itself. It was heavier, much stronger, much more durable, and capable of producing thousands upon thousands of molds. But, like everything, there was a catch. This pattern is a casting too. Think about that. The tool that makes the castings had to be cast first. That means that the master that produced this pattern had to account for the aluminum shrinking. Then, this match plate pattern had to account for every future casting also shrinking. Shrink, built on shrink. Pattern makers call that double shrink. It sounds simple until you realize every dimension on every surface has to be correct before you've ever poured a single production part. There was one major trade-off though. An aluminum match plate is incredibly durable, but it's also incredibly permanent. Before a foundry invested in building one of these, the casting design needed to be mature. Engineers and customers had to be confident that the dimensions, features, and geometry were finalized, because once the match plate was cast and machined, making changes became extremely difficult. Small adjustments could sometimes be made by machining or welding, but anything more than a minor revision often meant starting over and building an entirely new match plate from scratch. That made design changes both expensive and time-consuming, which is why foundries typically reserved aluminum match plates for proven parts that were expected to remain in production for many years. It was an incredibly durable solution, but not a very flexible one. And that challenge would eventually lead to the next major evolution in pattern making. Then, in the early 2000s, everything changed. Instead of hand tools, computers. Instead of drawings, 3D models. Instead of hand carving, CNC machining. We, here at Thomas Machine & Foundry, were one of the first foundries in the Pacific Northwest to begin machining production patterns in-house. Today, we're still one of the only foundries in our region that designs and manufactures production patterns entirely under one roof. These patterns start as solid blocks of urethane we call red plank. We glue them together into large blanks, load the CAD model, apply shrink, generate the machining toolpaths, and let the CNC remove everything that isn't the pattern. Here's what's truly amazing. Every cavity is identical, every dimension is repeatable, and every future pattern can be recreated from the same digital model. Need a design change? Machine away the old geometry. Glue on fresh material, program your changes, run the CNC again, done. That flexibility doesn't just save time, it also reduces costs. Instead of replacing an entire pattern every time the customer updates a design, we can often modify the existing tooling. That means less material, less labor, and far shorter lead times. It also makes pattern making much more accessible. Customers can make improvements during the development process without worrying that every design revision requires completely new tooling. For production parts, that translates to a lower tooling cost, faster turnaround, and a more competitive manufacturing process. What once required months of craftsmanship can now often be completed in less than 2 weeks, not because the work became easier, but because the tools became smarter. Now that you know where patterns came from, let's see how one actually works. Imagine for a moment you're a single drop of molten aluminum. Your journey starts here. This opening is called the sprue. It's the entry point into the mold where the molten aluminum is poured. Gravity pulls the metal down through the sprue into the gating system below. From there, the aluminum enters these larger channels called runners. Think of them as highways that distribute molten metal throughout the mold. Their size and shape are carefully designed so that metal reaches every part of the mold smoothly and efficiently. Branching off the runners are smaller passages called gates. These are the final connection between the runner system and each casting. The gates aren't just openings. They're carefully engineered restrictions that control how the aluminum enters the mold. By controlling the speed and direction of the metal, they help reduce turbulence, minimize trapped air, and improve the overall quality of the casting. Beyond the gates are the cavities. These are the exact shapes of the finished parts we're trying to produce. Every curve, every radius, every draft angle, and every machining allowance has already been built into the pattern. Once the molten aluminum fills these cavities, we've created the rough shape of the finished casting. But filling the mold is only half the battle. As aluminum cools, it naturally shrinks. If additional molten metal isn't available to replace that lost volume, voids and shrinkage defects can form inside the casting. That's where these features, called risers, become incredibly important. Risers are intentionally designed to hold extra molten aluminum. Because they're larger than many sections of the casting, they cool more slowly and remain liquid longer. As the casting solidifies and begins to shrink, the risers continue to feed fresh aluminum into the part, helping eliminate shrinkage and produce a sound, dense casting. When you look at a pattern like this, it's easy to think you're only seeing the parts. But in reality, you're looking at an entire system. Every runner, every gate, every riser, every cavity has been carefully designed to control how molten aluminum flows, cools, and solidifies. A great casting doesn't happen by accident. It starts long before the furnace is ever turned on, and it starts with a well-designed pattern. For over 200 years, pattern making has continued to evolve, from handcrafted wood to cast aluminum to CNC machine urethane. The materials changed, the technology changed, but the goal never did. Build the best possible tool, so every casting starts with precision. Next week, we're leaving history behind. You'll watch us build one of these patterns from scratch, from raw red plank material to gluing, machining, and the finished production tool. Subscribe to follow the series, and if you enjoy seeing how American manufacturing really works, you're not going to want to miss what's coming next.